Human societies operate as active relational networks. Influence shifts constantly, connections form and dissolve, and positions of power remain fluid. The philosopher Michel Foucault built his late theory of power on a structural distinction between two divergent configurations of these networks. The first configuration is what he called strategic relations. Here, power is a reversible exchange. Influence is exerted, but the subordinate party retains the capacity to react, to maneuver, and to resist. The second configuration is a state of domination. This is a frozen field where the channels of influence lock into place, structurally blocking any capacity for resistance from below. Foucault meticulously mapped the topology of these configurations. He could describe what they looked like, but he provided no formal dynamics to explain the transition between them. We are left without a mechanism for how a fluid strategic space collapses into a rigid hierarchy. Discovering the mathematical mechanism behind this collapse represents a major objective for both critical theory and computational modeling. It offers a potential bridge between the abstract study of power and the formal dynamics of distributed systems. Today, computational modelers try to detect that threshold using scalar metrics, single numbers like the Gini coefficient or structural averages, to quantify hierarchy. These three line graphs display structurally divergent configurations. If we track a 100-node network, a standard scalar index will return a single metric of 0.33 for all three. The first is a bimodal field. A large majority exists, but a distinct intact minority cluster actively maintains its distance. This is a healthy, active strategic field. The second is a momentary anomaly. Driven by heavy-tailed statistical noise, a single node transiently spikes in influence before snapping back to the baseline. The third is a permanent locked system, where an external hub has forced a structural bifurcation, paralyzing the rest of the field. These three states demand completely different responses. One requires no intervention. One requires waiting out an artifact. The third requires dismantling a hub. Yet the scalar mathematics treats them as identical. Compressing a multi-dimensional geometry into a single number destroys diagnostic resolution. It blinds us to the actual architecture of the network, making it impossible to identify when a system is genuinely approaching a state of domination. This 3D coordinate system deconstructs the relational field into three distinct structural operators to solve the scalar illusion: centralization, asymmetry, and dominance. Centralization measures structural concentration, how unevenly influence is distributed across all nodes towards a single center point. Asymmetry tracks directional imbalance. It measures whether a structurally distinct minority cluster can survive against the weight of a dominant majority. Dominance isolates absolute magnitude. It measures the ratio of the single most powerful node over the total weight of the entire field. The mathematics prove that these dimensions cannot be collapsed. Over a 500-step simulation trajectory, no weighted combination of these three operators can resolve structural conflation without losing critical diagnostic data. When mapped empirically, centralization and asymmetry exhibit high statistical coupling. They move in opposition, acting as dual projections of the exact same state field. Dominance behaves entirely differently. It occupies a mathematically orthogonal dimension, operating independently from the other two variables. To accurately measure power, we must track influence dispersion separately from the survival of minority positions, and track both separately from absolute monopolization. The empirical structure of the CAD vector maps onto Foucault's philosophical topology. The statistical relationship between these variables follows the logic of his three-stratum analytics. Centralization maps directly to Foucault's techniques of government, the specific institutional and procedural channels, like the architecture of a prison, that concentrate and direct human influence. Asymmetry maps to strategic relations, the ongoing agonistic structural imbalance between dominant and subordinate clusters. Foucault linked institutions to strategic struggles. Centralization and asymmetry statistical coupling proves this dynamically. They are dual aspects of the same active power field. Left to its own mechanics, institutional power naturally consolidates, formalizing human behavior into highly organized, unyielding pathways of control. But the final variable, the orthogonal dimension of dominance, tracks the threshold of Foucault's states of domination. The mathematical independence of dominance confirms Foucault's intuition. It behaves as a categorically distinct saturation property, structurally isolated from the strategic struggles taking place elsewhere in the field. Foucault predicted Cauer's geometric shape decades before complex systems mathematics possessed the tools to prove it. This unified framework sets up the final calculation. With the topology defined, the dynamical question emerges. Under what exact conditions does a system cross that orthogonal threshold and freeze into total dominance? The answer lies in the relational saturation limit, a mathematical theorem governing systems that operate in a regime of active metastability. In these systems, inherent noise guarantees a baseline level of variance. This acts like thermodynamic heat, keeping the influence field physically agitated and structurally open. In the mathematics, this noise floor is defined as axiom 3. It works in tandem with axiom 5, a recombination operator that continuously regenerates minority positions out of that persistent statistical noise. Tracking dominance reveals an analytical ceiling, the relational saturation limit. Due to these axioms, dominance is mathematically constrained, unable to reach absolute saturation. Even under extreme external pressure, forcing a hub to dominate, global dissipativity prevents that node from achieving full field saturation. Within distributed relational systems, resistance is a mechanical necessity. It is an endogenous mathematical property of the architecture itself. This creates a historical paradox. If the mathematics guarantee a structural ceiling, how do real-world regimes ever achieve total control? This structural model illustrates the corollary of joint suppression. Total saturation requires altering the physical structure of the system itself. If an authority suppresses only axiom 5, neutralizing recombination, the system loses its capacity to generate new positions, but the underlying noise floor persists, keeping the field actively resistant. If they suppress only axiom 3, halting the injection of variance, the true phase transition requires both. Only the simultaneous joint deactivation of both axioms causes the variance floor to collapse entirely, shattering the ceiling and freezing the system at absolute dominance. This mathematical transition maps directly onto the historical anthropology of David Graeber, who identified the specific social freedoms required to prevent tyranny. Axiom 3 represents the human freedom to relocate, to generate variance by acting unpredictably. Axiom 5 represents the explicit freedom to disobey, constantly regenerating resistance against the majority. Crossing into true Foucaultian domination requires a catastrophic phase transition. It is a state achieved only through the coordinated, simultaneous destruction of a system's baseline freedoms. The mathematics suggests but total control remains out of reach as long as the capacity for variance and recombination remains active.